going to start the last part of this lecture, which is centered on emphasizing application. We've learned the method. Now we want to see how this method can be used, what kind of problem it can solve for us. Actually, this particular problem is very important to me because it's not only an application. Actually, the whole method started from my study in wave, because I've been studying wave most of my research career. My thesis, PhD thesis, was on random wave, and after that I joined NASA. I still study water wave. Why I study water wave? Because after the landing of the moon, we want to look at the ocean, and the ocean is random. And then how you understand these random processes? Yeah. So that I study water wave all the time. But as at the beginning of the class, I say that I do have some problem with waves, and at that time I did not really emphasize the problem. I emphasized the what I have done. Now I'm going to point it out what's the problem, because without this course we will not appreciate this. The outline is, first I will review what we know about deep water wave. Then I will list on the problems that I think we have on the water wave study. Deep water wave, I want to first get a review. Water wave is one of the earliest natural phenomenon that successfully, quote unquote successfully, attacked by mathematicians. Yeah. In fact, the treatment of water wave was thought so successful. So in England, the water wave and the hydrodynamics took the central stage of mathematical study. Yeah. So in England, it's different from other countries. If you read, study mathematical history, you'll find that in the 18th, 19th century, there's almost no British mathematician. All the mathematicians are French and German. Why? Because Newton. Newton was so successful that he dominated. He said, listen, there's no way that you study mathematics, you have to study physics. And by study physics, then you actually, from physics, you study mathematics. And Newton also invented the calculus. And after Newton invented the calculus, he had a terrible fight with Leibniz. Leibniz was Germany. So Leibniz published papers. He says, no, look, I find the this calculus. Then once Newton found it out, he said, you steal it from me. So Newton accused Leibniz of stealing the idea from him. So of course Leibniz said, no, this is my own invention. What Newton has his point, because Newton invented calculus a long time ago. When he was in his 20s, he was still in college. But he hid it from other people. He never shared with other people. He will use that to solve problem, and then after he solved problem, he will use geometry to resolve the problem in different way. So people thought, well, Newton is really genius. How can he draw all this complicated geometry figure out the problem? So when Leibniz published that, Newton said, look, you have to copy from me, otherwise how can you find out this method? So Leibniz asked the Royal Society to make an impartial study to determine who invented the calculus. But he didn't know that the Royal Society was not very impartial, because the president was Newton. So Newton appointed a committee. The committee never met. but the final report was written by Newton and accused Leibniz of stealing. Yeah. But that's fine. The Newton won a big battle, but British collectively, England collectively lost the war, because all our notation are Leibniz notation. Integral signs, differential signs, dt, d theta to the n or whatever, that's all Leibniz notation. But since Newton thought I invented a calculus, so you have to use my notation. Newton's notation is x as a function, x derivative is x dot, x second derivative is 2 dots, and third derivative is 3 dots, and after 4 or 5 dots, especially without a very good pen, it becomes totally confusing how many derivatives you have taken. So the British stick with Newton's notation, yeah, and the continental follow Leibniz. And because Newton is so dominating, everybody is paying attention to physical problem rather than mathematical problem. They all try to return to physical problem, and that reduced mathematics almost to applied math. Yeah, and after Newton, water wave becomes a big thing. The water wave, for 100 years, for more than 100 years, water wave is dominated by Stokes. Who's Stokes? Stokes is this gentleman. Yeah, this gentleman actually, look at him, George Gabriel Stokes, the 1819 to 903. Yeah, he's a Lucasian professor. Lucasian chair was Newton's chair. Yeah, Newton's professor occupied that chair for 1 year. Then he decides, I'll give the chair to Newton. Newton is much better. So Newton's that chair, and then he occupied that chair. The current chair is occupied by Stephen Hawking, and he's president of Royal Society. See, this position were all occupied by Sir Isaac Newton. Yeah, and not only that, he's a genuine, bona fide mathematician. He actually established Stokes' theorem. It's a very important theorem in calculus. Nevertheless, all of this is started from a practical problem, like a hydrodynamic problem. And this hydrodynamic problem is treated as mathematics in England, in English system. And that this tradition of study hydrodynamics as mathematics, or elasticity, Hooke's law, and study solid mechanics and fluid mechanics, hydrodynamics as mathematics, is a very deep-seated tradition in England. And as a result, the English mathematics, the mathematics in England has never really developed as compared to France, as compared to Germany, as compared to even Italy. Okay, and this tradition was finally broken by Hardy, Hardy. Hardy is an interesting character, and he wrote a very beautiful book called The Apologies of a Mathematician. Yeah, it's a very nice book if you want to read. So, for 100 years, the British studied mathematics by studying hydrodynamics, and the mathematician, like for example, Stokes, he is a very good mathematician. Yeah, but he developed Navier-Stokes equation, which governs fluid mechanics. It's a fluid hydrodynamics. So he actually is the one that established the classical wave theory. What is the classical wave theory? Classical wave theory says that Stokes wave a periodic wave of permanent shape. He started as assumption. His wave is of permanent shape. If you look at a wave, the wave propagates, looks like almost permanent. It propagates away from you. So he started with a assumption of periodic, so one after another, after another, after another, and the shape never changed. And what is the solution? In 1847, he already proved this theorem. So 1847, he was still pretty young. Yeah, he like in previous, we can see that he was born in 1819. Yeah, 47, he's not quite 30 years old. He developed this, and he lived from very, very old age. And at that time, see, after he derived this theorem, he says water wave is a cosine theta. It's a cosine wave. So actually, Fourier expansion. Cosine wave is not enough. Then you have cosine 2 theta, harmonics, 3 theta, third harmonics, 4 theta, and so on and so forth. What is the theta? Theta is k dot x minus sigma t. What is 2 theta? It's 2k dot x minus 2 omega t, 2 sigma t. So harmonics is twice the phase velocity, phase function. Okay. Now when you have the phase function twice, because 2k, 2 sigma, so the phase velocity is still constant. So the shape never moved, never changed. This, because of his position and because of his proofs of mathematics, anything else, anybody study any other waves, they will regard as irrelevant because it cannot be right because this is the solution. And as a result, Russell Scott got the short shift because Russell Scott find a solitary wave. The solitary wave is a very important, much more interesting water wave problem. Okay, but because it's not permanent, because it's not periodical, they say, well, that's not important. Yeah, it turns out this wave now, it's not important. Solitary wave now becomes very, very important because solitary wave appears in all over the place. Now we will touch a little bit of that. What is solitary wave? Solitary wave are shallow water waves. Yeah, it's highly nonlinear, but in the 60s, an analytical solution was found for it, and that made it so powerful, and it can represent so many different phenomena. So once Stokes find this solution, everybody think, well, that's the only solution. Anything other than that, it's not important or not relevant or whatever. So this becomes the standard, is the classical wave theory. And classical wave theory is this. See, if I have a cosine wave, this is the this is the cosine wave. This is the cosine function. 0 equal to 1, 180 degree equals. What is the second harmonic? Second harmonic is twice the oscillation. 1 oscillation, 2 oscillation. If you add this to that, what you did is add here positive and here negative, and here again positive and negative positive. So from a cosine wave, it becomes this wave. And what is this wave? This wave is the bottom becomes flatter and the top becomes more pointier. Okay, this is only 2 terms. It's already, you see the asymmetry of the wave. If you keep adding, what happened in the end? In the end, you will have a sharp crested like a point and run off trough like a very smooth curve. And that's what the water wave get into the extreme. Yeah, and people are using the new symbolic logic. They can expand this Stokes expansion to 120 some terms and really get a very, very pointy shape. profiles. So this is the wave that governed the water wave study for 100 years. Nobody thought of anything else. And then something odd happened. In the 50s and the beginning of 60s, the SHIP division of National Physics Laboratory want to make a wave channel. And this wave channel is to study ship development. Yeah, different countries all want to build ships. And when you build ships, you want to know how much forces act on the ship. And to determine the force on the ship, actually wave is the critical element. Because you see, if the ship come sit on the crescent trough, the center part becomes a beam, and the wave, a lot of time the wave actually break in half. Yeah, and the wave can overtop, and the wave can cause the ship to rock and even overturn. Yeah, so shipbuilding always need a wave tank to make that study. And because the influence of Stokes, so they write a contract with a company. So you build me a wave tank, and the wave tank should generate water wave of permanent shape, so that you can study its consequences and the forces and all that. And what happened is that the tank was built, and the wave was generated, and they found that the wave propagate like this. It's very regular, but eventually the wave breaks down like this. It's no longer regular. And the National Physics Laboratory was so unhappy. They told the contractor, said, you have to correct this wave maker, or you have to correct the wave channel. Otherwise, we'll not give you money, because you did not create a wave of permanent shape. Yeah, this wave maker is defective. Yeah, or the tank has certain oscillation. So this then becomes such a big problem. Then at that time, in 1960, Professor Owen Phillips published a paper. Yeah, Professor Phillips is the Royal Society, is the National Academy of Engineering, and Professor Phillips is still alive. He happens to be my professor when I studied in the United States. I was his third student. Yeah, his first student is in England. Second student is in the United States. I'm his third student. What he did in 1960, he published a paper. The paper said that the theory on dynamics of unsteady gravity wave of finite amplitude. Okay, so previously we say the water wave of permanent shape, it's steady. If it's a permanent, I can measure it here, measure it there, and measure now, measure later. Should not make any difference. But he said that the dynamics of wave, it's really unsteady. Yeah, if the amplitude is finite. I mean, small amplitude maybe, but finite amplitude, it's unsteady. Now, this initiated a new era of wave study. That through the third order resonance interaction, is a much weaker nonlinear effect can actually change the wave totally, change the wave into a different form. Yeah. The paper was published in 1960, and I went to the United States in 1962. I studied structure theory, bridge and buildings and reinforced concrete, steel. But by the time I went to United States, I was put in Professor Phillips' laboratory. The laboratory is fluid mechanics. And why Professor Phillips' laboratory still has vacancy? Because Professor Phillips was not around. he was at Cambridge. Yeah, his laboratory has no supervision, and he just wanted to build a laboratory to study water wave, to try to verify that theory. In 1962, the theory was just published. Okay, so because I was assigned to the laboratory, so I switched to fluid mechanics. That's my career, a big U-turn in my career. And what he did was he said that because water wave is it's periodical, it has frequency, and the frequency is dispersive. So he find that if you have 4 waves interact together, it actually may generate a different component, and different component will cause the wave to be unstable and eventually degenerate. This is the famous figure 8 resonance interaction figure of Professor Phillips. And the Benjamin Fair immediately published a paper and suggested that the unsteadiness in the water wave tank is a natural consequence. And later it established that is a special case of a Phillips resonance theory. Now, that makes Phillips resonance theory so popular and so powerful, and established a total new modern wave theory. Yeah, start from 1960. Then, based on Phillips theory, then Hasselmann is a German scientist, immediately formulated in the spectral form. So Phillips only established one component, how they interact. Now, what if in the open ocean they get so many different components? So Hasselmann said, well, if you have different components, the different selective components, if it satisfies Phillips condition, and those components will interact and will make the wave to change. So he formulated this in 1966 and so on. And this formulation was based on the perturbation analysis. Meanwhile, in Russia, Zakharov, Vladimir Zakharov. Vladimir Zakharov now is the director of Landau Institute of Theoretical Physics in Moscow. He's a very powerful theoretician, and most of his work is in plasma physics. But when he looked at water waves, he said, I can solve that problem. So he solved it formulated in Hamiltonian formulation of the spectrum in spectrum form. So I want to show you his result. He said that the wave-wave interaction in the spectrum shape looks like this. To this day, I think perhaps you cannot find more than 5 people can actually go through this and check all the little signs to make sure that everything's right. I don't think there's more than 5 people can do that. Okay, but everybody believes this is new. This is correct. And you look at this formula. This formula has 3 integral, but integral is in terms of k vector. So that is actually 6-fold, because kx, ky has 2 components. So 6-fold Boltzmann integral. And if you try to evaluate this, it will take forever, especially in the 60s. The computer is not very good. Even in the 70s, 80s, 90s, even today, it's still hard to evaluate. Yeah. So nobody actually tried to evaluate this carefully. And you look at this T. This T actually gets spun out in this form. Okay. And in this form, it has V and has W. It's all V. V is another shorthand. See, V is this complicated, and W looks like this. So this is just unbelievably complicated formula. to describe the water wave. So people, this result is awesome because you cannot derive it, you cannot prove it right, so you have to say accept it, because if you cannot prove it right, must prove it wrong, it must be right, okay? And it's the math is so rigorous. And not only that, they actually made the first computation. This is actually what the formula express is how the wave from one component moves to another component. Okay, so if this is the peak of the spectrum, this is a higher wave number. It's slightly higher than the wave peak. The energy, you will lose energy. Where the energy will go to higher frequency, higher wave number to be dissipated, and also to lower frequency to make the wave grow longer. So this formula explains two things. The energy will be dissipated at a higher frequency and also to lower frequency, so the short wave can grow longer. It was so powerful, and to this day still dominate water wave community. Okay, water wave community was so successful that they say, I can predict wave, I can make a wave forecast. Give me wind, and I have wind blowing, and I can predict what the wave will be tomorrow. Yeah. Because they are so successful, well, at least they thought they were so successful, they hurt themselves. Why? Because if you can predict it, then you go to the funding agency, so give me more money to study wave, and the funding agency will study what? You can already forecast wave, you can already predict wave. That means you know it all. I don't have more money to study a problem that you have already solved. So after this, for 20 years, there's no money for wave study. Yeah. Until 1980, 85, I went to ONR and started a new wave program. Otherwise, the money is just simply dried up. So it was so successful. And not only that, and theoretically, they also studied the governing equation. And when we look at the governing equation, we start to find some problem here. Wave number equal to, we have some of this we have already touched. This is a touchback. If wave number, in all the theoretical study, the phase velocity, the phase function, they always say that there exists the phase function. The phase function is gradually changing. It's changing very, very slow, and gradually changes such that the spatial derivative is wave number, time derivative is frequency. So if you spatial derivative this and time derivative that, time derivative this, spatial derivative that, this cross differentiation, so then that becomes identical. So you add them together, this becomes zero. This is a wave conservation law. Everybody, every wave study book started from this point. But after this starting point, they throw it away. They never come back to check it. Yeah. What is the phase function? Nobody provided phase function for you to look. Yeah. What is the frequency? Nobody checked the time derivative of phase. Yeah. So they just assume that frequency exists. Okay. And if you look at this, the wave number and frequency has to be differentiable. Yeah. It'll be a continuous function. It has to have instantaneous value. Then it will be differentiable. None of the water wave frequency that they use by them now is differentiable. It's a continuous function. But that never deterred them from saying, I understand the wave completely. Okay. They don't. They think they understand it. Anyway. So that's here. And also you talk about energy conservation. group velocity up here. You cover action conservation, omega here, group velocity there. So for every wave study, you do need frequency as function of time, and wave phase velocity as function of time and space. But that has never been done. Okay, but at the 60s, people already derived these equations, and they think, oh, we understand the wave, no problem. We have conservation kinematics, we have conservation dynamic conservation, with all kinds of conservation. Yeah, and not only that, you compare these two equations. You see these two equations, what's the difference? Cg times E, this E. And you compare this with that's only extra omega. This time this is only extra omega. If this is right and this is right, and the only thing can be true is that omega is constant. Yeah, all kinds of inconsistency were buried in the equations, but nobody really checked. And for deep water, they even have a even fancier expression. So the fancier expression is derived in 1979, so almost 1980, of the nonlinear Schrödinger equation. Water wave, the governing equation becomes Schrödinger equation, and that created lots of excitement. It says, water wave now, Schrödinger equation is linked to quantum mechanics, so this must be the most fundamental and very, very deep. And the method he used was perturbation to the fourth order, and but in the derivation, sigma is constant, frequency is constant, and the equation come out to be this. What is A? A is not water particle. A is wave envelope. Yeah, so you draw an envelope of the wave. This is the envelope is governed by this cubic equation. Where's the cubic? Where's the cubic? All of these are linear. The cubic is here. A times A squared. Yeah, that's the cubic term. So by then, the study was so good. People thought that we have really solved some fundamental problem. And if you have Schrödinger equation, then Schrödinger equation has a recurrence. That means the water wave can be regular, and the propagate become irregular, and then come back to regular again. Okay, come back to the original state. In other words, the water wave can propagate and it can become highly modulated, and after the modulation, it becomes demodulated again. This is called the Fermi-Ulam-Pasta recurrence. This is a very important thing in nonlinear mechanics. Yeah, those papers were published, and people in the 1970s, 70s and 80s, they were so successful. What make all this study possible? Cold War. People, why would they want to study wave? You can predict wave and you still study it, because in the mid-70s, NASA sent a satellite which has a synthetic aperture radar. And when the synthetic aperture radar look on the ocean, they can see submarine. Even though submarine is deep in the water, but the surface has a signature, and it's caused by the waves. So Department of Defense and the CIA start to give a lot of money to study water wave in that connection. So the study was so successful, people thought that there's no more problem in wave. So clearly, wave, but in fact, if you look into that, you'll find that the waves are indeed nonlinear and non-stationary. Yeah, but by looking at the old wave, you will not find the problem. You see on the surface everything's fine. Yeah. So with this, I think we need a new tool, a new look. And even up to the 80s, people still think that in the 70s and 80s, the wave study was so successful, there's no more problem in wave study. So this is my problem. After I find the Hilbert transform, what is my problem? My problem are these following questions: how to define frequency? What is the physical meaning of spectrum? Yeah, in water wave study, everybody plot Fourier spectrum. What is the meaning of Fourier spectrum using Fourier transformation? Yeah, how the wave grow? Yeah, and then finally, is the directional evolution important? And all these problems start to appear, and especially after you look at the wave in a different point of view. Now, first look at the frequency. How to define frequency? As I say, even in wave study, frequency is defined as 1 over period, and that I think it's not right. The 1 over period, we have already said that it's crude. It's not going to work. This is the stuff that we cover in the class. Yeah, we know that. And we also know that it should be this. And we discuss that. Okay? And not only we discuss that, we give you a way to actually find the theta. Yeah? So the Fourier frequency and the wave number are all constant. That's the problem. If you have a constant wave number, constant frequency, it's not a function of time and space. And if you put in that equation, even though it does not violate the equation, constant derivative is 0. So the conservation law becomes 0 plus 0. And constant is not involving differentiation. So omega and c can all be taken out. So why you derive so complicated equation if it's all trivial? Yeah. So that is the problem. And whoops, what happened? So nonlinear wave, the frequency should not be constant. This is again the nonlinear view. Yeah. If we have a nonlinear system, then the pendulum becomes this or becomes that. Right? So how to derive that? How to describe that? We discussed this all in our class. Yeah, this is a review for you. And it becomes, the shape get distorted. Yeah. And so now we look at the water wave. See what the water wave is. In the water wave, we built it. This tank was built for me when I moved to NASA. Yeah. They want me to work for NASA. I say, well, sure, I will work for you, but if you build a laboratory for me, yeah, this is the laboratory they built for me. This total length is about 27 meters. Actually, now it's a little bit longer. We have made some addition at the end. Yeah, we modified this part. This becomes much bigger. And so it extends almost 30 meters long. And we have wind. We can blow wind in this tank. We can generate a water wave. We can even generate currents. So this makes a very good laboratory for us to study water waves. And a very simple experiment I did was to generate a wave, let the wave propagate this way, and using a wave maker, constant wave maker. So but 3 meters from the wave maker, I get a profile like this: 4 meters and 6 meters and 9 meters, 10 meters. By the time I get 15 meters, the wave gets totally disintegrated. It's exactly what the National Physics Laboratory got. Okay, so let's first look at this, the very regular water wave. See, this wave maker is made to oscillate so carefully. I drive this wave maker exactly as a sine wave. Okay, I drive this wave maker with a signal generator the frequency is set to 6 decimal accuracy, and I let the whole thing run for hours, so it's stationary, and it still looks like this. And if I look at this station, what I find is that this is the water wave. Water wave. If you look carefully, the crest is a little bit sharper than the trough. Yeah. And if you take a derivative of its Hilbert transformation, you find that the frequency is not constant. Yeah. Not only the frequency is not constant, it's not even symmetric with respect to the wave. Yeah. This is really surprising. This is the first time people have seen the instantaneous frequency defined as time derivative of phase, because previously they don't have phase. If you use sine, cosine, you don't have that. Yeah, this is the first time people saw this, and that's why when I first get this result, I went to Caltech to give a seminar, and after the seminar I said, "Wow, this is interesting. Why don't you come over here to do some additional research?" So I went to Caltech for 2 years to develop the Hilbert transformation method. Yeah. This is what we got. See, this change, this modulation is not small. If the modulation is small, then we may say, well, it's near constant. Remember, people assume frequency to be constant. Constant here is 2.5. It goes up to 3, come down to 2. That variation is not small. It's 20%, plus minus 20%. That's by any argument is not small. Okay, so the derivative is, the value is not constant, and the derivative is not small. And not only that, if you look at this station number 1, you look at station number 3, fluctuations get even higher. And if you average over all the waves, you see all the wave profile looks like this. It's slightly skewed. See, this is 0.05. This is the center. The peak is slightly forward. Okay, the frequency is not constant. It's 2 to 3. And and you look at wave number 3, station number 3, it's more scattered, and the frequency is still not constant. And this wave becomes increasingly non-stationary. Yeah. So water wave is indeed non-stationary, and the frequency is not within one wave. It's not constant. It's indeed nonlinear. This data really proved the two properties of water wave clearly. And if you use wavelet, when I did this was in the early 90s. And early 90s, wavelet is still on the rise. I mean, to this day, probably wavelet start to flatten out. In the late 80s and early 90s, wavelet is the rising star. Okay, so everybody has to use wavelet to prove their case if you are serious. Now, this is the colorful thing is the wavelet. It gives you the frequency modulation. You see, the frequency is modulating, and that is amazing. If you use Fourier, you'll never see that. Okay, using wavelet, you indeed see this, and the modulation. Look at the modulation. The modulation is there. Not only that, if you look at it very carefully, the modulation is not actually symmetric. In other words, the peak of this does not agree with the peak of the modulation. So the wavelet, if you read it carefully, you see a lot of quantitative suggestions of the property. And and the frequency, the frequency is over this range. Why it's over that range? Because wavelet has a priori base, so it needs harmonics. These are all the harmonics. And if you use Hilbert, the Hilbert says no, the frequency just oscillates like this, and it's slightly skewed toward the front. This kind of result convinced a lot of people that Hilbert is better than Fourier. Yeah. And so now we know that the water wave, the frequency should not be defined any other way. Not by Fourier, not by wavelet, and not by any other method. Yeah. And we have the tools now to do it. Now the second problem is, what is the spectrum? Yeah. Now, what does the spectrum represent physically? Yeah, especially the spectrum based on Fourier transformation. Does it make sense? Now let's see. Fourier, again comes back. It's a great method, and this method has a problem because it cannot describe variation with respect to time. And this problem, for example, it has to reduce to harmonics. Yeah. And harmonics is oscillate. In fact, the frequency is oscillating. They give us harmonics. That doesn't make sense. And and for nonlinear waves, the distorted wave, it has to have harmonics. The principal, the fundamental wave, harmonics, 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 harmonics all over. Yeah. Now for Hilbert, it does not. So now, what is the implication? The implication is this. If I take the previous wave, the water wave, that very regular water wave that you see station number 1, if I do a Hilbert spectrum, what I got? I get fundamental peak at 1, 2, 2.5. I'm very happy, but that's not the end of it. I have harmonics, 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 harmonics. I have all kinds of harmonics. Why I need harmonics? Because the water wave is not linear. The waveform is already distorted. Yeah, and this harmonics, add to simulate the sharper crest and runoff trough. Okay, if you go to say station number 5, it has still since a peak has a sideband and harmonics again, and even you go to the 8th, you have peak slightly shifted, and you still have harmonics here. This is the peak, this is the harmonics. So all of this are harmonics. In other words, the high frequency part of the wave spectrum are populated by harmonics rather than by real wave. Why harmonics has a problem? See, having harmonics, that means the water wave, if you have harmonics, it means water wave is nonlinear, right? Now, in the ocean wave, the crest of breaking wave need many harmonics. The breaking wave starts like that and sometimes even turn over. And that becomes so complicated to represent. So Fourier spectrum is full of harmonics. It's impossible to separate the harmonics from the wave. Now let's first look at the water wave. The previous record is the wave that I got from the tank. So now I go to the open ocean. This is a wave measured in the open ocean. Okay, wave measured in the open ocean. How do we measure it? This is a float. You put a float in the water and you have an accelerometer. So the wave drive the float bob up and down. So you measure the acceleration and integrate it. You get this wave profile. This wave profile and this actually cover 1 hour, and it's 1 hour data. You take that data. There are 4 ways to represent it: Fourier spectrum, wavelet, and Hilbert. Yeah, just like a voice, we have different ways. So this is the so-called narrow band. I use 512 data points. So each of this, the frequency is very well defined, but the time is smeared over that length. And this is with time very well defined with 32 points, but frequency is smeared. But both of this suggest that we have a frequency around 10 hertz. See, no, it's 0.1. this is a 0.1 hertz. That means 10 seconds. Yeah, it's a 10-second wave. 10-second wave turns out to be very common because the average wind over long time average over the open ocean that generates a wave that propagates very long distance around 10 meters, and that generates around 10-second waves. Yeah. Now you use wavelet. You see, we also have energy, the highest energy along this area. That's again 0.1 hertz. It's 10-second wave. You look at this, we also have around 10 hertz, 0.1 hertz, 10-second wave. So all of the four representation all give you roughly the same frequency representation, but the impression you got is totally different. Yeah, which one is better? Now we know these two have problem because the uncertainty principle. You don't know which one to try, which one to use. You cannot narrow down the frequency. You cannot narrow down the time. Here you say, aha, I can narrow down the time, but the frequency actually is smeared vertically. Yeah. Over here, it's so dotty, so scattered. So if you compare this with that, everybody probably, most of the people, if not everybody, will pick this one as the better representation because it's so clean and so nice. So when I present this, I always say, if we have a beauty contest, this one won. Yeah. But what are the physical details? What are the information they can give us? Let's see. If I plotted the wavelet in contour in minute detail, the wavelet in contour is this line, or this line. These are the wavelet analysis contour, and this black contour separates spotty representation that represent each beam, whether we have data or not have data. Okay, this each beam actually are the Hilbert representation. Now let's first point it out. The two agree. Why the two agree? When you have a lot of contour, we have a lot of Hilbert has lots of energy. See, any heavy contour have lots of Hilbert energy. So the two agree, at least qualitatively. But quantitatively, they are different. The Hilbert does not have a bloom, a smooth smear thing, because it has to be smeared because it has a priori base. It has to use the sideband, the harmonics in order to fit the profile. Okay. Not only that, let's also see. This is the wavelet contour, just as before. Let's take the Hilbert spectrum away. Let's just plot the wave profile. Okay. Now you see the wave profile. Here we have a very large wave, and this large wave has a longer period. So we have a lot of energy and very low frequency. And after that, you see, after this couple wave, you suddenly have some short wave. The frequency suddenly increase. Yeah. So the wavelet people, when they first come out, they were delighted to see this, because you will not be able to represent that in the Fourier analysis. Because you can, if you want to pin down the frequency, you have to smear time. You want to pin down the time, frequency smear. So you will never be able to see this kind of change. So this is a big victory. This is a triumphant parade for wavelet. Yeah, and the energy large and frequency decrease. And you can see that when frequency is high and this goes up, over here you have a longer frequency, it's dropped. Longer frequencies drop. It's beautiful. Yeah. qualitatively. Now let's see how this compares with Hilbert. The Hilbert, it's that these few waves, you know the frequency precisely, not over this range, but here, right there. Not only that, when the frequency suddenly changes, it immediately goes up, and frequency down immediately comes down. It does not smear, it does not average, it does not provide a smooth picture. It gives you the punch by punch, point by point study. This is I have already reduced into bin because I processed this data a long time ago and I don't have enough memory. I believe this was done with 386 computer. And if you redo this, you can put in as many bins as you want. You can probably see a lot of more details in the wave frequency modulation and energy modulation. So when I first saw this staggered dot, I was a little bit worried. I said, gee, the Hilbert is not as good. But when I make this comparison, I found the Hilbert is so precise to actually track the frequency. See, you go to here, this is some small frequency, immediately comes up. And the energy is small, so the contour is light. Yeah. So you have all the detailed quantitative information. Now you plot the spectrum. The nice, beautiful wavelet, it becomes so smooth, the spectrum becomes sad. It's hardly useful because it contains no information, almost, other than the peak. That's it. Yeah, everything is smoothed out. And this one is the Fourier spectrum. The Fourier spectrum has a slope, and that slope at the beginning of the class I talk about -5, -4 is based on that slope. And that slope is the Fourier-based spectrum study at the beginning of the course. Yeah. What we got here is the Hilbert. The Hilbert does not have all this frequency. All of this is because you need additional small wave to fit the wave profile. It's not wave, not a real wave. Yeah. In fact, all the higher frequency part of the spectrum is mostly populated by the harmonics. It's not a real wave. Yeah. Here we have wavelet, Hilbert, and Fourier. So, free wave versus bound wave. What is free wave? All water wave is dispersive. What is dispersive? Dispersive means that the propagation speed is a function of wave number or frequency. Where did that come from? In the equation of motion, if you derive it, you'll find that in water wave, frequency square equal to gk. G is gravitational acceleration, k is wave number. Yeah. This is the dispersive relationship. The wave frequency and wave number has a relationship, and that relationship is called the dispersive relationship. Why? Because phase velocity, by definition, is wavelength over wave period. One wave passed, how long it passed? Average. Okay? And because 1 over L is wave number, 1 over T is omega. Yeah, see, 1 over T is omega, 1 over L is wave number. So phase velocity equal to omega over K. Yeah. Now given this, and also by definition phase velocity equal that, so C equals to omega over K. Now with that you have G over omega, right? So this omega squared equal to GK. Yeah. So what that tells us? That tells us that the phase velocity, as the frequency gets lower, the phase velocity gets faster, higher. Yeah. What is low frequency wave? Low frequency wave are the longer wave. longer period wave. And that's why before the typhoon ever arrived, you will see the big swell first come from hundreds of miles away. It first arrived because the small wave does not catch up with it. The large wave first come, and gradually the shorter wave will come, but first comes the long wave. So in the 50s, people always realized that, but then the measurement was not good enough. So in the 50s, Hasselmann and those people make a big name because they go out in California. They measure water wave frequency. They find that the frequency today is very long. Tomorrow it's become shorter and even shorter and shorter. So they measure a couple of days. They say, aha, the longer wave arrive first, and it takes so much time for the shorter waves to arrive, just so they can deduce where the wave come from. Yeah, this is just like a group of people with different running speed. We know their running speed, and we let this group of people start from one given location, let them run. At the beginning, this group is tied together, and as they run further and further, the distance becomes longer because the faster runner and slow runner, the velocity difference is given. So as time develops, this distance is going to get longer and longer. Yeah, the so-called dispersion. And the group at the script was able to deduce where the wave was generated. And turns out those waves are generated in the Southern Indian Ocean. And that makes a big splash. That means the water waves are not locally generated. It can generate all the way to the other side of the globe and still propagate all the way to Scripps Institute. Yeah, from Southern Indian Ocean to North Pacific. Yeah, it propagates so long, so far away. Yeah, so that's all because of this. C equal to omega over k. Omega over k can be, using this, you can write omega squared equal to gk, so g over omega. Then you take this omega as the square root of gk, you put it in, half of the g cancels out the g over k. So in other words, if omega and k are small, then the wave phase velocity are higher. Okay? So dispersive relationship dictates that the different wave number propagate at different speed. However, if we have harmonics, what happens? 2 theta means 2k x minus 2 omega t. So what is the phase wave number? Wave number is 2k. What's the frequency? Frequency is 2 omega. So 2 omega over 2k is still omega over k. So that harmonics wave propagate at a fundamental wave velocity. And that guarantees the wave profile does not change drastically. However, that means that the shorter wave is 2 omega propagated to C, not the G over 2 omega. Okay, so that wave cannot be dispersive. Because you put the 2 omega here square, it's a 4 omega square. And it's only 2k equal to 2k. That violates this. This is a fundamental physical equation. So the water wave spectrum, if you plot it out, you'll find that the water wave spectrum, higher frequency part, is totally different. It cannot be physical wave. They are bounded waves. Yeah. See, harmonics are not dispersive. The higher frequency range of the spectrum is usually populated by this bounded wave. The bounded waves are not physical, they are mathematical. They are not physical entity, but mathematical artifacts. If I use different mathematics, I will have different harmonics. Yeah. And if it's fundamental physics, it cannot be different. Yeah. So, so this is the problem. This is the problem. Why we have the problem? The problem is with integral method. Integral method, as I said, if frequency is not a function of within the integral limit, so So the frequency variation is not continuous. Yeah. And the a priori base need harmonics. So this integral transformation also suffer uncertainty principles. So if you have not taken this course, you will never understand this view graph. You will never understand what I'm talking about. Now you understand. You say, yeah, you think back, you'll find that the frequency has to be instantaneous and it cannot be integral. And why it cannot be integral? Integral not only integral has the following problems in describing the physical properties. Yeah. So this is the. So I'm going to use this application as a review of the course, as well as pointing out how to apply this method. Okay. So the next thing is wave evolution. I talk about the wave spectrum has a problem. Okay. Talk about frequency has a problem. Talk about wave evolution. Wave evolution is very important physical problem. That is, how the wave grow and how the wave die. Yeah. We use the fact that we use the word grow and death. That means we have already personified wave. We thought the wave is a person. And the person is small, little kids can grow big, and as they're getting older, will eventually die. Yeah, mature and eventually die. Are the wave really person? And the wave really grow? That's the kind of problem that we want to answer. Why we think wave will actually grow and die and evolve is because when you have wave data, you find that this is a wave spectrum, Fourier spectrum, measured from the coast out, from Delaware Bay. It's near near where I used to work in NASA. They use aircraft. The aircraft fly out. On the aircraft has a very nice radar. The radar actually map out the whole surface. You can get a directional spectrum. We'll talk about that later. What it finds is that near the coast, the waves are very high frequency. The frequency is so high and amplitude is so low. This is for offshore wind. The wind is blowing offshore from the coast. And as you go further, the wave becomes bigger and get longer and propagate faster. The frequency decrease and decrease and decrease and decrease. And not only decrease, as when the frequency decrease means wave get longer, and when the more energy means wave get higher. So you wave start from a tiny little wave, get a bigger and bigger and bigger and bigger and bigger. So they say, well, gee, this really look like a human being, from a little baby grow to a big tall guy. Yeah. So this is the wave growth. Yeah. Now, how to describe this? Yeah. To describe this, as we say, that's by the Hasselmann's thing. And not only that, we got problem also too. The wave from regular wave modulate and come back regular again. We say that's Fermi-Ulam pasta recurrence. And that was published, and everybody believed that it recurrence. But now, when we look back, what do we find is this. See, this wave, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, not quite 6. Yeah. This wave is much shorter than that wave. So the wave from here to there, after the turbulent, demodulated period, it actually grows. Yeah, again, like people, after going through the rebellious teenager, getting a regular human being, regular mature guy. Yeah. So the wave actually, when it grows, it not just come back to the original. It actually grows longer. And you can have this experience if you stand in front of any body of water, a pond, a lake, or even a water puddle. Yeah. When the wind blows, you see the beginning part, the wave is shorter, and then at the other end, the wave becomes longer. But the wave moves so fast, we cannot follow up with our eye to see how each wave gets longer. So that is one of the questions we want to answer. How to get longer? We see here, originally interpreted as recurrence, from narrow band spectrum to narrow band spectrum, going through a wide band stage. Yeah. But when you come from here to over there, the frequency changed. The wavelength changed. It actually did not go back to the original, but it get longer. What happened? Yeah, this is 3 meters, that's 25 meters. Yeah. So let's see. If every wave survived and every wave get a little bit longer, is that possible? Yeah. Why we say every wave survived? Because the wave conservation law said the wave cannot be destructed. If wave cannot be destructed, then every wave have to grow a little bit, right? Every wave survives, and then each and every wave have to grow a little bit. So suppose this wave grow a little bit, and this wave also grow a little bit. So this wave becomes the second wave, has to move over here. That means this wave has to move that far. And if each wave grow, then each wave needs a little bit more room. So then this wave will have to move that far, and this wave have to move that far, and this wave have to move that far. Is that possible? No. Why? Because waves are dispersive. How fast the wave moves is dictated by its frequency. Yeah. For this particular frequency, wave can only move that far. It cannot, some wave move further than other wave at a given time. It's not possible. Yeah. Like, for example, I don't know whether you have the experience. If we, when I was young, in the morning we all stand in form to raise the flag, and then the teacher or the principal will give us a short lecture on the moral issues, like how you should study hard and how you should behave yourself and all that. After that, we have an exercise session for 10 minutes. So when you stand to listen to the teacher, everybody stand very close to each other. When you exercise, you have to have a little bit distance. So when we say form the exercise formation, then the guy near the center does not move. The guy next to it moves 1 step. Next guy has to move 2 steps. And at the end of the formation, have to move, say, 20 steps. So this guy cannot just move 1 step. They have to run away. Yeah. Now, if everybody's movement is a given velocity, we cannot have this. Right? This is not possible. Yeah. This is not possible. Then, so to evolve spontaneously, it's not possible, because the wave, because of the dispersion relationship. So, and that prevents the wave from, say, spontaneously evolve. Now, how about continuous growth? So, like people start from little wave, getting bigger and bigger and bigger and bigger and bigger and bigger. Yeah, continuously, not spontaneously. So is that possible? The continuous wave movement is like covered with this and armed with Hasselmann's formula. Draw a curtain over there. So what happened over there? It's over this. If you don't understand that, well, take that for granted. Then the wave, a small wave, will grow big. What's the problem with that? We still have problem. The problem is that look at this side. If before this curtain, how many waves come into the curtain? There are many, because see, at a given time, each wave period is given. So in a given time, how many waves get in? This unit time divided by t. This frequency. right? So how many times does the wave pass in unit time? That's how many waves get behind the curtain. How many waves come out? Very few. That means a lot of waves come in behind the curtain, only a few waves comes out. Where the other waves, what happened to the waves? Yeah. What happened to the wave have to conserve? Yeah. So that is another problem. So we have to answer, what happened to all these waves? See, 10 waves move in, only 1 wave come out. What happens to the other 9 waves? Yeah. That is a legitimate question that we have to ask. So the wave number has to be conserved to pass through control volume, and if that violates, then we have to ask, we have to track all the other waves. And if we cannot account for the other wave, we have problem. So continuous evolution also has problems. So now let's see what exactly happened. What exactly happened? We come back to this experiment again. This experiment has this wave evolved to that, gradually evolution. This is the real thing that happened, and I recorded. And if I took this wave, traditional view, as I said, is plotted spectrum. You see all the spectrums, peak is still there. This one, only this one, the sideband, see, starter has a little sideband getting bigger. What it means sideband getting bigger? That means the wave, instead of constant amplitude, when you have sideband, start to beat. Yeah, have very close frequency, the wave amplitude start to be modulating. And modulating getting bigger and bigger, eventually this band getting bigger. That means the lower frequency, the frequency getting low. When did this happen? Only at the 8th. What happened to the 5th? The 5th is nothing, still peak and has 2 sidebands. Yeah, means modulation getting bigger. You cannot say, you cannot detect when the water wave will getting longer, okay, or whether the wave actually get longer. So if you look expanded, so 3, 4, 5, 6, yeah, this is 3, 4, 5, 6. You cannot see this modulation, this is peak, this is harmonic. You cannot see exactly how the individual wave change, because it only gives you the average. Now, let's have the Hilbert view. Yeah, we will talk about the Hilbert transformation. That's when I get started. I have this question. I want answer, and I cannot find it from Fourier. So I turn to Hilbert. Yeah, and what Hilbert give me is the phase velocity, phase function. Yeah, the phase function looks like this. It's from 0 to 60 seconds, the record, and the phase function all the way increased to about 800, 900. Yeah, the phase function is continuous changing, 2 pi up to 2 pi, 4 pi, 6 pi, and all that. Now, the derivative of phase function is frequency. Now you see, the first station is here, the 8th station is there. This slope is steeper than that. So then I look at this and say, the frequency indeed changed. Yeah, at least on the average. So I was very happy, so I see the frequency change. But how it changed? It looks very gradual, with a little bit nutty, but it's on average, it's almost, if you draw a straight line, looks gradual. So I decided to examine this a little bit further. The way to do that is to use the first station as a reference. Yeah. If I use the first station as a reference, I take the difference always the first station. What happened is that the first station minus first station is perfect. So 0, 1 is 0. And other station minus that, the first 4 station is all here. That means the phase velocity, this is in radian. It's almost 0. A little bit of fluctuation, but not much. Okay. But when you come to the fifth station, then drastic thing change. Drastic thing happen. At here, at the phase function suddenly dropped to this level and dropped again to this level. And each of this drop, amazingly, is 2 pi. That means at each location, one wave disappeared. We lost a wave. Yeah. The wave does not grow, it does not grow continuously, does not grow spontaneously. Some wave suddenly get wiped out to make room for other wave. And this is totally violate all the equations that we discussed. And this is so shocking to me that the wave can actually disappear. Yeah. Now you look at others. You go to the another next station, it dropped and stay in this level. This level is around 6. That's 2 pi. And then drop, come to here. It's around 3 pi. Drop another pi. Every drop is not arbitrary. It cannot drop a fraction of a pi to drop exact 2 pi. Not only you look at this, another presentation of this even more clear. I plotted here the phase modulation. I plot here amplitude. So I plotted station number 2. Station number 2, the amplitude oscillate up and down a little bit, but the phase difference relative to station number 1 is never deviate from 0. I come to station number 4. The amplitude fluctuation is much bigger. Okay, but the phase is still 0. That means the phase doesn't change. I still have the same number of waves. You come to station number 5. You see the phase stay in 0, stay in 2 pi, stay in 4 pi. Only in those even number of pi's, 2, 4, 6, 8. Never in between. Never in between. The amplitude fluctuation is much bigger. And even you go to the station number 8, you see this jumps to that, jumps to that, jumps to that. Every jump is 2 pi. And that really, without this Hilbert transformation, I will never see such details. Yeah. And this give you magnifying glass, give you quantitative answer of how wave change, how wavelengths change, and where the wave disappears. Now, we will even examine this even closer. I plot here station number 5 profile. Then I plot station number 1 profile in the background as a comparison. Okay, so you see all this wave line up. That means this wave are one-to-one correspondence, even though the amplitude may modulate a lot, but the frequency basically did not change. Now when you come to this, you see, it's still one-to-one. But when you come to here, this frequency suddenly dropped 2 pi. At the frequency that it dropped, 2 waves becomes 1 wave. Yeah. So one of the waves disappeared. Which one disappeared, I don't know. Yeah. But one of the waves disappeared and becomes 1 wave. This wave takes the place of 2 waves. Now, by the time I studied it, to this point, I realized that this is a totally new phenomenon. The wave actually fused together. 2 waves becomes 1. Then I started checking into the previous publication. Other people have counted the total number of waves. They find that indeed the wave disappeared. They call it missing crest and whatever. But they have never systematically pinpointed the exact location or how many waves actually lost, because they don't have the tool. They can only look at the data. They say, aha, if you look at the data, you see this wave is a little bit wider. Yeah. Now we have a tool, and this tool is Hilbert transformation. This tool gives us exact location and exactly one wave missing. So the wave can actually fuse. And if you go to other place, you see that this wave line up, this wave line up, here it dropped 2 pi. And over here, this wave line up, this wave line up. In the place of this wave line up, in place of 3 waves, it becomes 2. So 2 becomes 1, 3 becomes 2, and so on and so forth. Eventually, the wave gets longer. The wave gets longer, not uniformly, but locally. Not continuously, but discretely. And that's something which has never been observed, which has never been reported. Yeah, people may report, one wave lost, but they have never pinpointed n to n minus 1. Yeah, that is how the wave actually change. Yeah, 3 to 2. Yeah, this is again a case of line up, 3 wave becomes 2. Yeah, so all the wave actually change abruptly, discretely, locally. It's not a global thing. If it's not a global thing, we cannot use Hilbert. We cannot use Fourier. We have to use Hilbert to actually see this. So the wave actually fuse. Yeah, the waves behave a little bit like particle. They are discrete. When they fuse, 2 wave becomes 1 or 3 wave becomes 2. The change is not continuous but local, discrete and abrupt. This acts very much like particle, and that gives me some doubt. See whether this process can be described by partial differential equation, which is continuous derivative and the slope is small and all that. I very much like to continue this study. This was done almost 10 years ago, and that's actually the start of HHT, start of this Hilbert transformation. And when I try to go back to do the laboratory, because I moved away from the laboratory to a different center, and I give the laboratory to one of my PhD students, ask him to take care of it. But the equipment gets older, the probe breaks down, and I will never be able to get the kind of data I need. Yeah, to this day, I still want to continue this, but I don't have the facility. Yeah. I asked my student to collect some data for me, and the data he collected was so noisy that I cannot do anything. Yeah. So I hope in the near future I will be able to go back to the laboratory and collect another set of data to prove not only this changed, I want to prove whether the action is still conserved. The wave number is not conserved. Whether in the process we conserve action or conserve energy, or what is really conserved. Yeah. The wave number conservation is off. Now I'm going to check each of the conservation law to see whether they are still stand. Yeah. That's my goal. One of the goals of this study, the physical study. I start from wave, and I really want to go back and check to see whether the conservation law is still true. I haven't seen any good facility around. Maybe there's one facility in Cheng Kung University. They built a huge tank, but I don't know them well enough to ask them to do this problem. Especially, they may not be very friendly to this problem. They still think of Fourier spectrum is good enough. And if you want to tamper with their fundamental, they may be a little bit apprehensive. Yeah. So we'll stop here. Next time we'll start with the governing equation, and we'll continue to study the direction with development. So this, and after this wave study, I will talk about bridge. I'll talk about aircraft. Okay. If we have time, we'll talk about other things. These are all applications. If we have even more time, we'll talk about the human body, biomedical. Okay? All right. Thank you very much. By the way, any questions? I forgot to ask you. I was so carried away. When you get old, your memory is always with the past. So when you talk about this, it's full of memories. And when I first get this, and when I first get the result, and how excited I was. Yeah, go ahead.
The result is, it means when the wave propagates, the wavelength will be longer and longer. But it only happens locally, not globally. Is that what you think? Because before they always use correlation form. They sort the phenomenon, the longer phenomenon is global.
Yes, they actually think the average wavelengths change. In other words, everybody change. Just like a student from first grade is so short, and second grade everybody grow longer, and third grade still higher, and by the time you get into college, everybody's like they full grown. Yeah, that's the Fourier view. But here you see it's not that way. However, after the local growth, it grow here, grow there. Eventually, at a certain stage, like the recurrence, then every wave is a little bit longer. So in between, some waves are longer than others.
So only the longer phenomena only happen in
Yeah. It's like either here. See, locally this wave is much longer than all the other waves. But using Fourier, it's averaged out. See, this wave is longer than this wave. See, these two waves are longer than that wave. Yeah. Using Fourier, we never see it. But we have demonstrated. If you use Hilbert, you immediately spot it. Right? So this is why Hilbert is so important, because it's like a magnifying glass. Minute change, I can spot. Yeah. If you don't have this, you only getting average. You can get a statistic answer. This is not a statistic answer. This is the quantitative, local, and discrete answer. Yeah. More questions? This one?
It's kind of squeeze this way. This move from this to this, and this kind of, I don't know, in this block, you feel like the kind of shift this way to the, I don't know, just, and the same thing here. Also shift a little bit to this side.
No.
And so the frequency
this
here
does not perfectly line up. This shift a little bit, this shift a little bit. But this drastic shift of these two waves, right? And this wave has shifted a little bit. There are little bit shift. This little bit shift is modulate this modulation.
I'm assuming that squeeze that side there will be higher frequency near the peak.
Near this peak.
Yeah, because it's kind of.
Well, this peak shift a little bit. This peak shifted.
Yeah.
So they are a little bit modulating. Small modulation exists, but it's not like this big jump like that. Question? No. Any more question? Any more discussion? See, from now on, it's all application. Every time I will call your attention back to what you learned. Okay. All right. The class is dismissed.